Okay, you are really going to like this one. Here we have an is equal to an minus 1 plus an minus 2. And this is like a Fibonacci sequence, right? And we have this 3 years ago already. So here I'm going to add a little bit more flavor. Namely, right here I'm going to add an minus 1 times an minus 2. And because we have this times that, in fact, the whole thing now it's not linear anymore. And the truth is, it's really hard to solve a nonlinear recurrence relation. We just have to be really lucky sometimes. This right here is actually solvable, so let me demonstrate. Have a look right here. I will have to use a blue marker first though. Alright, here's the deal. If you look at this as how it is, unfortunately, the usual strategy of an equals r to the n, and then just go ahead and substitute, this does not work. This works if we have a linear situation with constant coefficient, right? It works. But unfortunately, with this in mind, no. So maybe we have to get rid of this. But the truth is, if we didn't have these two terms, if we have an is equal to an minus 1 times an minus 2, that actually can be solved pretty easily as well. How? Well, we like to solve linear, right? That's a product. Just take the natural log on both sides. Then actually end up with log of the first plus log of the second. And you can use a linear situation on that. Very good. So we are going to somehow get rid of the first two terms. But how though? Well, here we have something times the other. I want to produce the negative of the first and then the negative of the second somehow. This is how we can make it happen. Let me demonstrate. We are going to start let bn equals an plus 1. In another word, you can look at this as an is equal to bn minus 1. Well, have a look. Right here, an is equal to this, which is bn minus 1. That's equal to a sub n minus 1. You just have to put the subscript right here, which we get b sub n minus 1 and then minus 1. And then you do the same thing, so plus b sub n minus 2, and then we have the minus 1 after that. Yep, so far so good. Well, now the interesting thing is that right here, we will have to do this times that, and we have the negative. They will help us to cancel this and that. Very good. All right, so continue. We add parentheses. Well, for this is bn minus 1, the subscript, and then we have to minus 1 after that, and then we multiply by b sub n minus 2, and then minus 1 like this. Now, focus on this right here. This times this, we get bn minus 1, bn minus 2. This times this, we get minus bn minus 1, subscript, right? And this times this is minus bn minus 2. This times this is plus 1. This can be cancelled out with that. Very, very nice. Likewise, this and that, isn't it? Of course, if you would like, minus 1 plus 1, sure, why not? Have a look. In fact, here we have bn minus 1. And we also have the minus 1 right here. This can be cancelled with that as well. So in fact, we successfully reduced to the situation that bn is equal to b sub n minus 1 times b sub n minus 2. Like that. Very, very nice. And then again, we can actually turn this into a linear situation by after taking the logarithm. So let's go ahead and take the natural log here. Likewise here. Well, the left-hand side, we just have ln of bn. And then on the right-hand side, well, the log of the product, it's a sum of logarithm. So I will just write this as ln of b sub n minus 1. And then we are going to add ln of b sub n minus 2. Like this. Now, if you would like, you can do another substitution of sequence. All you have to do is, you can call this right here to be Cn. Well, Cn is equal to log of b sub n. So this right here is just going to be Cn minus 1, isn't it? Yes. Likewise, this right here is just going to be C sub n minus 2, isn't it? Yes. This right here, we get back to the original Fibonacci sequence form. Very good. And if you haven't noticed already, notice how I put down A1 and A2 to be E minus 1? Because for that, I did that on purpose. Have a look right here. Okay, this is what we have to solve now. And perhaps let's just get the general form first, and then I'll tell you guys what C1 and C2 should be accordingly, alright? With this in mind, let's go back to the black marker now. With this in mind, I'm just going to start off by saying Cn is equal to r to the nth power, because here we have a linear situation with constant coefficient. Then as we can see, with this, we can just go ahead and plug in. You will see that we get r to the n. That's equal to c sub n minus 1. With this form, we get r to the n minus 1. And then we add r to the n minus 2. Now, everybody has a factor r to the nth power, right? And then we will end up with r to the negative 2 power right here. So let's go ahead and multiply everybody by r to the positive 2. So if you would like, I can show you guys some work. This right here we multiply by r to the second power, and in the meantime divided by r to the nth power, just like that. So you actually end up with r squared, and this right here will be r, but let's bring that to the other side, so it becomes minus r. This will be 1, bring that to the other side, becomes a minus 1, that's equal to 0. And we have a quadratic equation. Then we are just going to use our quadratic formula, because why not? Right here, negative b becomes positive 1 plus 1 minus square root of b squared is 1 minus 4 times this times negative 1, which becomes positive 4, right? And then of course, negative 1 squared is 1, 1 plus 4 is 5. So here we have 5, and yes, divided by 2. And yes, we have the golden ratio and its inverse. And you might be wondering, which one do we take? Do we take the plus or do we take the negative? And the answer for that is we take both, because we need both equations, because this right here is a second order difference equation. So have a look. Based on all this, I can tell you guys that Cn is in the form of the first root right here is just 1 plus square root of 5 over 2. So this is our r, and then we have to raise this to the nth power. But this right here is just like your building block. You will have to multiply by a constant. And unfortunately, I don't want to use c because c is going to be crazy and all that stuff. So I'm just going to use, let's say, alpha right here, right? And then I'm going to add, likewise, we have another root. So I'm just going to put the minus down right here, which is 1 minus square root of 5 over 2, and then raised to the nth power. And I use alpha over there, so right here I'll use gamma. No, just kidding, right? Just kidding. Beta. All right. Oh, sorry. This looks like 13. Doesn't look nice. All right. Much better. Now, have a look. This is the general form for the sequence right here, Cn. And this right here is actually the Fibonacci sequence. And you'll see. Now, let's do this in our head. When A1 is equal to E minus 1, well, you put it right here. That means B1 will be E, the number E, right? And then if you put E right here, that means C1 will be ln E, which is 1. I did that on purpose. So with this right here, I can tell you C1 is equal to 1. Likewise, C2 is equal to 1 as well. Again, you put that here, there, and then there, right? Well, here, let me show you guys an easy way to solve the Fibonacci sequence right here. If you have this right here, you can of course plug in and then just solve the system equations, up to you, but perhaps you can also kind of go back a little bit. You can say C0 is equal to 0. Why? Because 0 plus 1 is equal to 1, and you can just go backwards. With this being in mind, of course, I can just put this down for you guys real quick. I can say 0 is equal to, put a 0 right here, this will be 1, and this right here will also be 1, meaning that we will have alpha plus beta is equal to 0. And then I will just put the 1 right here and right here. So this end, 1 and 1, and this right here will go here. So this one go here, we have 1. Then we will just continue alpha, and then this is 1 plus square root of 5 over 2 to the first power because of this. And then likewise, you just do the rest. Plus beta, and then 1 minus square root of 5 over 2, and then raised to the first power like that, all right? And now, elimination is easier. So now, have a look. And of course, from here, you can see that alpha is just the opposite of beta. In another word, we know alpha is equal to positive 1 over square root of 5. So with that being said, we can of course draw in the numbers accordingly right here, and right here. This right here is our Fibonacci sequence. Very nice. And now we just have to go back, and then we'll be done for this, right? Okay, this is our Cn, and of course we know that the natural log of Bn is equal to Cn. So have a look. Natural log of Bn is equal to all this. So how can we get rid of the natural log? Of course, we do e to this power and likewise e to that power, right? And as you can see, we pretty much will have Bn, I'll put this down in blue because I start off blue with that. Bn is equal to e to the exponent. The exponent is just the Fibonacci sequence formula, right? So I'm just going to write that down right here for you guys. Okay, finally, we know that Bn, of course, is the same as Am plus 1. Well, in this case, how can we find out what An is? Of course, just minus 1 on both sides. So, ladies and gentlemen, the answer to that, I think I'm just going to call this the Fibonacci sequence on steroid. Because, oh my god, it's just crazy. Anyway, An is equal to e, and then we have 1 over square root of 5 times the golden ratio 1 plus square root of 5 over 2 to the nth power, and then minus 1 over square root of 5, and then we have the 1 minus square root of 5 over 2, namely the golden ratio wanna be to the nth power, and then after all this, the minus 1 is just a regular minus 1. It's not in the exponent, right? So, ladies and gentlemen, this right here is the answer to our original nonlinear recursion. Yeah, very cool, huh? I told you guys were going to like this. Anyway, let me know what you guys think. And again, you just have to be really lucky in order to solve a nonlinear recurrence relation. Alright, so wish you the best luck whenever you have to solve one. Anyway, as always, that's it.
Black pen, black pen, red pen. He's a calculus teacher, uses black and red. He does math for fun. If EQs get done, using complex numbers, doing marathons. And as always, that is